there wasn't an angle given, and then also one of the
Oh.
numbers had a step forward related one. We talked about it a little
Yeah.
bit, but the disk has an angular velocity,
Mm-hmm.
and it's connected to all the other parts. Those
Oh,
have an angular velocity.
they do, and you have to figure those out. So let's talk about that. That's a pain. Okay, so yes. Okay, I will do probably not the whole problem because it takes forever, but yeah, I'll try to get the main things that are unusual about it. Well, here's what will be on the test is the concept that I think that helps you solidify. You know what I mean? But a problem that long will not be on the test. That's for sure. Yeah, right. That's what. Yeah. Okay. Yeah. Okay. So you can. So I'll do it now, and then you can look back and see if what I says contradicts what I said last semester on the notes. Okay. So. Basically, what has to happen what happens when one body in a linkage has a given angular velocity but not the others. Well, the angular velocities of bodies in a linkage are not always, but sometimes related. They can be dependent. So to figure out the angular velocities, to find the omega vectors for the bodies that aren't given, you're going to just use the same idea as the joint constraint. So this time it's going to involve the velocities, not the accelerations. Okay, so this problem, there's a member like that. I gotta move this. There's a member this is supposed to be perpendicular to the first one. And that's connected to a disk. We're going to assume that these are the same height. This is 90 degrees. This is 32 degrees. This is 58 degrees after you do the trigonometry. And that's a pin. This length is 1.2. This is 1.8, and it's connected to that first member. I'm going to name these. So that's 1, 2, 3. It's called a 4-bar linkage because the ground is the fourth member. This distance is 0.9. And this is 0.9. The disk has an angular velocity of, well, right, is a vector. If our coordinate system is oriented like this, then the angular velocity vector of the disk is 0, 0, -5. Okay, and so we know that, so here's where that constraint idea comes in. And let me name these pins too, I guess. This is called A. I guess I'll call that B and C, and this fixed one I'll call D. Okay, so what we know is that because of that pin joint, the velocity vector at C, according to member 2, has to be equal to the velocity at C according to member 3. Okay. And we know that the velocity at B according to member 1 has to be equal to the velocity at B according to member 2. Okay. So we're going to work our way backwards that way. There's one thing one thing's easier than than the constraint equations, easier about this than the constraint equations, and that's that the velocity expression for circular motion is simpler than the acceleration one. The thing that's more of a pain is we don't have any velocity variables that are already in like a list of variables, and so we have to figure out everything relative to the ground. Okay, so first, let's do this one that's like, so let's do the one at joint C. So what's that going to say? This joint, the center of the, I guess I'll call that E. That point E there is fixed, right? Looks like it. I think it's supposed to be. Yeah, that's right. It had, so the ground is that fourth member, so yeah, it has to be fixed. And so figuring out the velocity of the point C according to member 3 is easy. Let's do that one first. So okay, so the velocity. Mm-hmm. It is. Seriously? Okay. Actually, that doesn't make it any harder. No, that's good. Yeah. So the velocity of that point C, according to member 3, is equal to omega cross r. The omega is the one that we know, 0, 0, negative 5, crossed with, that instant it looks like that r vector is just vertical. And so that r vector, the radius of the disk is 0.5, and so this is just 0, negative 0.450. And so that's negative 2.2500. But now we have to do it for member 2. And member 2 doesn't have any fixed point, so there's no point that we can assume that the velocity is 0. So the velocity of B relative to the ground is the velocity of the velocity of B relative to we're trying to find sorry. So the velocity of C relative to the ground is equal to the velocity of C relative to the joint B plus the velocity of the joint B relative to the ground. And this is circular motion. This one is circular motion of that. So we're going to be adding 2 circular motions. One is the circular motion of this part of the arm around that point B. Okay, that's the velocity of C relative to B. And one is the circular motion of B around D. Okay. So the velocity of B relative to the ground is omega cross r. What we want there is the angular velocity of 1. So that's 0, 0, omega 1 crossed with the r vector that goes from D to B. Anybody have any questions about that? What I'm doing there? Right. Or just the overall flow of how I'm calculating the velocity of that point C. And what do you get if you take that cross product? Negative 0.72 omega 1, right? Yes, thought so. And then 0.96 omega 1, 0. Well, this is the 1.2, but 1.2 times, yeah, because, yeah. And now we'll have to do it with the r vector that goes from B to C. So the velocity of C relative to B is 0, 0, omega 2 crossed with 0.5472, 0. And that one is positive 0.72 omega 2 and positive 0.54 omega 2, 0. And so the velocity of C, according to member 2, is these two things added together. That's the relative motion equation. So we have negative 0.72 omega 1 plus 0.72 omega 2 for an x component. For a y component, we have 0.96 omega 1 plus 0.54 omega 2, and then 0. And now finally we can set up that constraint equation. So we have two useful equations. We have negative 2.25 is equal to negative 0.72 omega 1 plus positive 0.72 omega 2. And 0 is equal to 0.96 omega 1 plus 0.54 omega 2. And we can solve that. It wouldn't be too hard to do that with substitution. We like to do it the hard way, so let's do this. So there's our equation 1, equation 2. There's omega 1, omega 2, the constant. So negative 0.72, positive 0.72, constant is negative 2.25. Equation says 0.96, 0.54, 0. So can someone calculate omega 1 and omega 2? Okay, so omega 1 is 0, 0, 1.125. Omega 2 is 0, 0, negative 2. And omega 3 is 0, 0, negative 5. Okay. And actually, so I said you needed to use both of those joints. Apparently, we didn't need this one. So in this forward bar linkage, if you specify the angular velocity of one of those bodies, that prescribes the angular velocities of the other two, and you have to figure out what those are. Yep. Any questions about that? What are we going to need those angular velocities for? Definitely stuff. Finding, yeah, the watermelon equation for finding the accelerations for the constraints. Yeah, that's, yeah, I mean, and so this problem is nasty. There's just a lot of stuff, but understanding that idea is important. So, yeah, well, understanding, I guess the thing we don't have to use for that, but you do have to use for linkages sometimes, is the fact that you can't just, I can't arbitrarily say, oh, this, you know, with some linkages you can, you know, like an open linkage. I could say, okay, this one, let's say that's spinning at 5, this one's spinning at 10. But with something like this, if I prescribe one of them, I can't give you other angular velocities. It wouldn't make sense with the body. Question? The 0.1? The, the 0.05, the 5 centimeters from the edge of the disk? Okay. That came in when we calculated the R vector from the center of the disk. That's just saying that that bolt or whatever, that pin isn't connected all the way at the edge of the disk. So that R vector, instead of being 0, negative 0.50, is 0, negative 0.450. Okay, yeah.
Oh, what angle did you use when calculating the R vector
from B to C? I used, well, Tim just gave me those answers, but I guess you could do it this way. This is the way I like to think about it. Yeah, I've heard enough out of you. Okay, so this angle is 32 degrees. That doesn't, let me draw that again. This angle is 90 degrees from the first one. And so you go plus 32 minus 90. So that angle is minus 58. Oh. Yeah. I needed to figure it out on my own. Yeah.
So you just use the negative cosine sine.
Yes. Mm-hmm. So then, I think that's really the only thing that's different from this problem than the other ones, besides the fact that there's just more of everything, more pieces and stuff. But now there are 3 bodies where you're going to use Newton's laws. Bodies 1 and 3 both have fixed points. So you'll get one equation from this, from rotational Newton's second law, one from this, rotational Newton's second law. And then you have one that doesn't have any fixed point. And so that one you have to do about the center of mass. And so you get 1, 2, 3, 4, 5 equations from Newton's laws. And then you'll do constraint equations at 2 joints. You'll say that the accelerations have to match here, and the accelerations have to match here for the 2 bodies that connect it. And so you'll have 5 plus 2 plus 2. So I guess it's a system of 9 equations for 9 variables. Any other homework questions? Okay, so let's get into what's listed. I was planning to be our last topic, but I guess things have moved pretty quickly this semester.
Day off.
Yeah, I don't know. I mean, I was sort of thinking about it this weekend, like we're going to probably finish this topic with time left in the semester. I mean, a class or 2. Yeah, well, yeah, right. I don't think there's any reason to like push more topics. I mean, if we have extra time, we'll just spend it doing problems, working on stuff together, just get a little more ready. Yeah, pizza party. You can study. Yeah, you can study while you have pizza, but please don't turn in any papers that you've written while you've been eating pizza. Okay. Yeah, that's fine. Yeah, that's the box.
I don't know.
Okay. Oh, is it? Oh, okay. Yeah. Sure. Uh, so now we're going to talk about mechanical vibrations. Um, and these can occur in any system where I'm going to call it a restoring force. It really could be a couple too, but um, there's a restoring force that pushes a system back towards equilibrium. Um, and so, some simple examples are the one I'm going to use for the derivation, where you have a cart on a spring, and if you move it and let it go, it'll oscillate back and forth. And do you know actually that these are basically the two ideas that all timekeeping was done with before uh, before there were like solid state electronics and whatever. And it's pretty amazing actually how accurate systems can be based on springs and pendulums. Um, so you basically, in both cases, it's a torsional spring that they use, um, not a linear spring. But in either case, what they do is you have a big source of power, which can be either a mass slowly dropping or a big thick spring, that torsion spring that's been wound up. And you have this little lever system that just increment by increment allows a little bit of the energy of that power spring to run out of the power spring through this system of gears. And the same thing would apply here. Give this a little nudge, and then it'll say, if you nudge it this way, it'll move back and come forward based on its own frequency. And when it comes back, it moves the hands of the clock or whatever. And same idea with big clocks, So the spring idea was used in pocket and regular watches, wristwatches. And the pendulum system is used in clocks because you can't carry a pendulum around in your pocket.
Why not?
You could. You could. And yeah, you could, if you wanted to be really cool, like, I feel like a big part of what I'm trying to do here is help you be cool when you get to the U, because or wherever, because like some of those study groups will already be, you got to sort of force your way into the study groups, and so you could calculate the length of the string you need your pendulum to beat, so it ticks exactly 1 second, and then you could just count the seconds to keep time. Just carry this pendulum around. But you wouldn't be able to talk much because you'd be counting a lot of seconds. But yeah, exactly. That would be a very like vaudeville kind of thing. Yeah, exactly. Everybody, no one would be like, it wouldn't be like, hey, you know that new guy? Like, oh yeah, the guy that's sort of tall but has, yeah, maybe it's blonde hair, whatever. It wouldn't be like that. It'd be like the guy who carries the pendulum. Like, oh yeah, I know who you mean. Yeah, exactly. um, I've been at the U. That's how it would go. That's exactly how it would go. Um, we'll do. Actually, I've been at the U more than like anyone else in the history of the U. I I took my first class there as a junior in high school and took my last class there when I was 34 or something. They should, but they're too impersonal to notice stuff like that. You know, they still don't know who I am. Yeah, exactly. Oh yeah, yeah. Um, so we'll discuss just 1 degree of freedom vibrations, and the ideas apply to more degrees of freedom. So 1 degree of freedom. Yeah. Um, systems. 1 degree of freedom just means that, so something has 1 degree of freedom if you could figure out a way to represent its position using a single variable. Okay, whether it's an angle or a linear position, a length from something. But if you can represent the position with one variable, that's a 1 degree of freedom system. And we're going to start with free vibrations. And then forced vibrations. And then damped vibrations. That's not. Yeah, when your dryer starts vibrating, that's what's going on. Damped vibrations.
What about vibrations that happen in electric power? Those are damp vibrations.
That's true. That's true. Yeah. Okay, so let's start with free vibrations, and this is really going to give us the basic differential equation that this is all going to be based on. So the underlying ordinary differential equation, when we add forces to it and damping to it, that's just going to modify this equation, make it more complicated. But say there's a spring connected to the wall and a cart connected to the spring that rolls along the ground. And the cart has a mass m and the spring has a constant k. So what can we say about the resulting oscillations when the cart is moved, somewhere away from equilibrium and released. So that's what we're trying to figure out. Well, a free body diagram of this system would have the weight, mg, and a normal force, n, and then a spring force. And if we say x equals 0, you know, the cart's at x equals 0 when the spring's at its resting length. We have to think about the direction. So we're going to have a magnitude of kx. We know that much about springs. And then we have to think about the sign. Okay, so if this cart has a positive x value, that means from its equilibrium position, we move it this way. Okay, move it, you know, push it this way. What direction is the force going to be that the spring applies to it? The opposite way. So from that, we think that's probably negative. Imagine the other case, move it this way. X is negative, the force is positive. So could have just drawn that as a pushing force with a positive kx, but I usually think of springs as like default tension or whatever, so that's how I do it. And so Newton's second law from this says 0n plus 0 negative mg plus negative kx 0 is equal to the mass times the acceleration, and we know the acceleration is just going to have an x component. We're trying to figure out stuff about the oscillation, which is all happening in the x direction. So we really only care about the x component of this equation. So we get negative kx is equal to ma, or ma plus kx is equal to 0. Bless you. And we're trying to figure out what we want really is we want to come up with a function, not what, want, x as a function of time. Okay. So the acceleration is the second time derivative of the position. So we can write this as, you know, divide both of these. So this is divided by m. The differential equation says x double dot plus k over m x is equal to 0. So this is the main differential equation. We can generalize this. You know, not all systems that oscillate have a spring constant and a mass in them. So we're going to call square root of k over m. You'll see why that is in a minute. Omega sub n, and we're going to call that the natural frequency. It's not actually a frequency, which is a pain when you're trying to keep this stuff straight, but that's what people call it. And then the equation becomes x double dot plus the natural frequency squared times x is equal to 0. I'll call that equation star, and that'll come up a bunch in this. I'll call this one equation 1. That's the one that's specific to the spring and mass system. And so how do we solve equation 1?
Equation 1.
Let's do it with equation 1. Equation 1 is equation star for this specific. So equation 1 is the more specific case that we're dealing with. Okay, so how do we solve equation 1? Well, one thing about differential equations is the hard part is coming up with the form of the solution. And so a perfectly valid way to solve differential equations, any kind of differential equations, is to just guess what the form is going to be. And if you're lucky and you guess right, you did it. And it's easy to check whether it works, So if I say, let's say x is equal to t squared, then I can take the second derivative of t squared, do this, check. In that case, it wouldn't work. So, we have to keep looking. But all I'm going to say, I'm going to pretend like we just guessed that this form so we're going to guess that x is equal to some constant a times the sign of the quantity square root of k over m times t plus the angle phi. Where a is the amplitude and phi is called the phase angle. One of the problems that I'll give you is just going through this derivation for something other than a spring mass system. So you just need to understand kind of how this works, but you're always going to take the step of just assuming that the form is, in general, this form would be a times the sine of omega sub n times t plus phi. So now that's the solution. We'll talk about how to get these constants in a second. Oh, no, we won't. We'll talk about it next time. But you can use boundary conditions to find phi and a. But what does this tell us about the rate of oscillation? Well, what we want to know is just like how long it takes. It's going to be steady in time. Like an hour later, it would still be oscillating at the same rate as at the start. What does this tell us about the rate of oscillation? We can think of that two ways. They're equivalent information, just expressed differently. The period of the oscillation or the frequency. Well, we know one period, and that's represented by the Greek tau, is when the change in square root of k over mt plus phi is equal to 2 pi. Okay, we don't care what it starts at. We just care that it starts to repeat itself, and we know that with a sine function that happens at 2 pi. And so you can think of that as, if you're taking a change and you have all this stuff at instant 2 minus all this stuff at instant 1, and so that phi is going to go away. And what we really want is we're trying to find where square root of k over m times tau is equal to 2 pi. So the period of the oscillation is 2 pi times square root of m over k. Okay, that's the period. The frequency, so the period is how many seconds per oscillation. Frequency is how many oscillations per second. So so the frequency f is just equal to 1 over the period. And so the frequency is just equal to 1 over 2 pi times the square root of k over m. So for spring mass, the spring mass system, if you want, so to oscillate faster, period gets smaller and the frequency gets bigger. So if you want the oscillation to go faster, how do you change the mass? Do you increase or decrease the mass? Yeah, so decreasing the mass leads to an increase in the frequency. And then what about the spring constant? Do you increase or decrease the spring constant to speed up the oscillations? Increase K, and that gives you a decreased, no, it gives you an increased frequency. Okay, so if you have a big heavy mass and a flimsy spring, it takes forever for that spring to turn this big mass around. If you have, oh yeah, yeah, that makes sense. And if you have a really stiff spring and you put a tiny little mass on it, it'll oscillate really fast. Okay, so I guess that's it. Next time I'll talk about how to use the boundary conditions to get those constants, and then we'll talk about other, like, you can actually have 1 degree of freedom systems that are not as simple as this. They just still have 1 degree of freedom, and we'll talk about calculating those.